Hello class, welcome to today's video, sections 2.1 to 2.2. While you're watching the video, make sure you write down any notes. Feel free to pause, rewind, replay, or fast forward as you need. Make sure you write down your summary of the video in your notes, and then make sure you submit your online WISC with summary and top question that you have to ask or contribute. All right, let's begin. So you may or may not know that velocity is the change of distance with respect to change of time. So as the change of distance may be a positive number, or the change of distance may be a negative number, then that means you can have either positive velocity or negative velocity, or if the change of distance is no change, then you can have zero velocity. And that's a numeric value that you may be familiar with from earlier on. But if we talk about the speed of an object, we use the velocity, but we use the magnitude of the velocity. In other words, the direction, whether or not they have positive velocity or negative velocity, is not as important for speed. It's just the quantity, the amount of the change that is of significance. And so in that sense, the magnitude of velocity is always going to be a positive number or greater than or equal to 0. So why is this important? Well, we're going to take a look at two types of velocity: average velocity over an interval and average velocity over a point. Now, in this particular case, the interval, of course, is closed, and it contains endpoints for x, or time is equal to a and time is equal to b. So we're not necessarily dealing with the independent variable of x, we're dealing with the independent variable of t, which is for time. So to compute the average velocity of an object over an interval from A to B, assuming B is greater than A, then we basically take the change in position or distance as S of B minus S of A, where S is a function that represents the position of the function over time t, and we divide it by the change in time. In other words, the difference between A and B. So the average velocity of an object over an interval is basically the net change in position during the interval divided by the change in time. And it should be very familiar to you because it looks very much like a difference quotient that we've been working with for a long time, which involves change in y values over the change in the x values. So to represent that, it's easy to see. And in that case, let's take a look at the different type of velocity, not over an interval, but at a point, a particular point in time. Let's call it A. And we call this type of velocity instantaneous velocity. So if S is the position function of an object at time t, the instantaneous velocity is defined as a limit of the difference quotient, as the change in time approaches 0. Okay, so let's take a look at what h can be looked at. If you remember, b can be represented as the original number a plus some change from a to b. And if we're considering that b is greater than a, then more than likely h is going to be positive. So the closed interval ab can also be represented as a comma a plus h, where h is the difference between a and b. So when we take a look at our original function in the denominator of the difference between b and a, that really is literally the value h, where h is the difference between a and b. So let's take a look at what this represents graphically, this instantaneous velocity, where we're taking the limit as h approaches 0 of this difference quotient. So we first take a look at, here we have a general curve function, and then we take a look at the interval between 1 and 3.5. And as we can see here, here's my point for t equals 1, and here's my point somewhere up here for t equals 3.5. So the average rate of change basically is the slope of the secant line through the through the curve at the endpoints of 1 and 3.5. Then if I want to take a look at a closer interval, let's say from 1 to 2, here's my 1 point and here's my 2 point, then that means I have another secant line because it has a different endpoints, and I take the slope of that secant line. And if you can notice, the difference in slopes between the yellow secant line and the green secant line is the green secant line is a little bit steeper. So what happens if we even take an even closer interval? We get closer and closer and closer to the point 1. In other words, our difference in our endpoints gets smaller, then it would assume that we would get a closer approximation to the velocity at that point. And that's exactly what happens. What you have is that average velocity at a point can be calculated by doing something very simple, by basically taking the slope of the secant line at the point. Now, your book talks about taking the slope of the curve at a point, and even though that may be difficult to understand, that curves do have a slope, but it's the same thing as the slope of the secant line. So how you want to take it, it's up to you. You can either consider this instantaneous velocity as the slope of the curve at a point or slope of the tangent line at the point. Both of those are perfectly good explanations. And in fact, your book talks about the average velocity over any time interval instead of just at a point being the slope of the line joining the points on the graph, which we know to be the slope of the secant line. Okay. So we talked about two different types of velocities, average velocity over an interval and an instantaneous velocity. And that's in the case where we have an independent variable of time. But what if the independent variable is not time? Then we no longer really have a real life situation of average velocity or instantaneous velocity, because our independent variable doesn't have anything to do with time. It may be over a different quantity. So we're going to change our terminology to include the situations where we're not dealing with the independent variable of time. So if the independent variable is not time, then instead of an average velocity over an interval, we now have an average rate of change over the interval. And instead of an instantaneous velocity at a point of time, then we now have an instantaneous rate of change at a point x equals a, not necessarily involving time. So if we change our gears and start looking at an independent variable that's not time, then our definition for average rate of change is very similar to the definition for the average velocity over an interval. Instead of from a to b, we're looking at an interval from a to a plus h, where h represents the difference between the two endpoints of the interval. And as you can see, since our function, which is no longer the position function, is a general function f, then we still get a difference quotient of the difference in the output values divided by the difference in the input values, which looks very similar to the slope function that we've been dealing with for a long time. And if we want to try and find the instantaneous rate of change, then we would do the exact same thing, but in addition, we would add a limit to that difference quotient. And the limit is going to be as the difference in the endpoints goes to 0. We call this the derivative of your function f at that point a. It's basically the exact same thing as the rate of change of f at a. And if the limit does exist, then f is said to be differentiable at a. If the limit does not exist, then f is not differentiable at a. Let's take a look at a picture that's found in the book, and very similar to the previous picture is if we take a look at just an average rate of change over an interval, and here the interval is from a to b, in this case a to a plus h, then the rate of change between this secant line, i.e. the slope of this secant line, is found by taking the change in the y values, f of a plus h and f of a, and dividing it by the change in the h values. And if we want to look at a specific rate of change at a specific point, then as we make the difference in intervals smaller and smaller and smaller, then we're going to get different slope values until we get to one that really reaches when the limit of h, or i.e. the difference between the values, approaches 0. And we get a more defined value with more accuracy. So any way you look at it, the derivative of a point can be interpreted either as the slope of the tangent line to the curve, because as we move the values between a and a plus h, as we move the difference between those two endpoints smaller and smaller and smaller, you no longer have a secant line. As we saw, these were secant lines. You end up having a tangent line because that's ideal in this situation. And so we can represent the derivative of a point at a as the slope of the tangent line to the curve at a, or the limit of the slopes of the secant lines at A, or the slope of the curve at A. So the last thing we're going to take a look at is how to evaluate the derivative at a point, either graphically, numerically, or algebraically. In other words, how can we find the derivative of a function at a point x equals a? So let's take a look at the sine function, and more importantly, as x is equal to 3.1415, or pi. Okay, so what we're going to do graphically is to see what the rate of change of the secant line and tangent line is going to be as we zoom in. And this is where they start talking about the slope at the curve. And as we zoom in closer and closer to 3.14, what kind of shape is the function now looking like? It's looking like a linear function with negative slope at this point. And if I were to try and calculate the slope of this point, so if I say here's my point pi comma 0, and let's pick another point, 3.12 comma 0.0216. And so graphically that ends up being a slope that looks very close to negative 1, because it's negative 0.99999. If I would get a closer interval than 3.12 to pi, then I would get a more closer approximation. Now let's take a look at this numerically. We take the sine of x1 minus sine of pi over x1 minus pi, that same difference quotient, and we look at values as they get closer and closer to pi, and we see numerically what's happening to the values of this difference quotient. It seems to be approaching negative 1 from the left side, and it seems to be approaching negative 1 if we're coming from the right side as well. So numerically, the slope of that secant line ends up being close to negative 1. Graphically, and therefore it ends up being close to negative 1. Let's see what it looks like when we do this algebraically. And here it is algebraically, trying to find that answer. So we convert sine of pi plus h into the addition problem, and we get sine of pi times cosine of h plus cosine of pi times sine of h. And then we evaluate sine of pi and cosine of h to be 0 and negative 1 respectively. So we get that that is really the same thing as limit as h approaches 0 of negative sine of h over h, which we know to be negative 1. And if you don't remember, refer back to examples 1 and 2 in section 1.8. So we have been able to find the limit or the derivative of the function sine of h at the point x equals pi in 3 different formats: graphically, numerically, and algebraically. Thanks.